So welcome to week 11. And now we are returning basically home to our solar system. So this week and next week is going to be about our solar system and exoplanets and how we investigate the stuff. What do we know roughly about the working of our sun? Or we know where the energy comes from, but how is it then built up from the inside to the outside? And then we will also go through the planets. So next week I will have a bit of a focus. When can a planet have an atmosphere? What is necessary? Why are we so lucky on Earth to have an atmosphere where there is no greenhouse effect, where we have water? Go to big Jovian planets, so the gas giants. And then we go, how is it investigated that there are planets around other suns? But let me start with the slides. Okay. So what you see here is Voyager 1. It's one of the two Voyager probes that has no or depends on the definition of the solar system, but it basically has left the solar system. Then there are the two Pioneer probes, which are on a good way to do so. And these are basically, or at least the Voyager ones, are the first man-made objects that left the solar system. The good thing is it's still reporting data. It's mostly sleeping mode, but it's still also reporting data. It has a plutonium battery, which is going to work for quite a long while. But now it's going through the interstellar medium. So let's see, maybe it has us more surprises. Okay, so our solar system again, so back how we basically know it from the very first lecture. We had it already a bit. Now we come back. So the big dictator is the sun. So this here is, of course, everything not to scale. And the inner planets, the rocky planets, Mercury, Venus, Earth, Mars. Here comes the asteroid belt, and in the asteroid belt is Ceres, a dwarf planet. And then the four gas giants, Jupiter, Saturn, Uranus, Neptune. We will find comets. We find other dwarf planets like Pluto and Makemake, Eris, and so now we could say what is the solar system, and we would basically look, for example, the old Pluto orbit, which is very eccentric in terms of an ellipsoid, more than the inner planets. So here we see also with Eris, it's clearly an ellipse. So, and we're going to learn about another object that is even more going further away than Eris. There's the Kuiper belt. And this is now looked from above. If we would look from the side, we would see that the 8 planets, they orbit basically nicely in a plane. But for example, Pluto doesn't, Eris doesn't. The Kuiper belt is twisted towards this plane. So, but the cross structure would keep go this way. And outside of the Kuiper belt, there's this Oort cloud. So clearly the major body in the solar system is the sun. It contains 99.85% of the matter. What have we known so far from the sun? Well, if you remember, we know its energy at the moment comes mostly from fusion of hydrogen. To a very low degree, so about 2% come from the C&O cycle, where then carbon acted as a catalyst to fuse 4 protons in the end to a helium nucleus. Where do we know this from? These were the solar neutrinos that tell us our models are not that wrong. Then its surface temperature is about 5,700 Kelvin. But I think there is no writing mistake, which I later need to correct. Where do we know this? Well, if you remember, I've shown you from this satellite that basically recorded the Planck spectrum of the sun. This was also relative at the beginning. But then the maximum we can associate with the temperature. Soon we're going to see it consists is a plasma. So we don't have a solid or liquid. It's a plasma, ionized gas, which consists mainly of hydrogen, to some degree of helium. So 3/4 at least are hydrogen. Roughly almost a quarter is helium. And then for a star, we have already a considerable amount of other heavier elements, carbon, oxygen, magnesium. So very likely from this abundancy, very likely it's a 3rd generation star. So that the material that is in our solar system is very likely undergone already 2 supernovas beforehand. From the Hertzsprung-Russell diagram, we know it's a relatively average star, slightly above average in terms of the mass and the brightness, but still fairly average. We live about 10 billion years. This is all from this Hertzsprung-Russell diagram. But where do we know about this elemental composition, at least on the surface? Of course, we look at the light. And then we have from the inner shells basically a Planck spectrum, or it's a wide spectrum that comes. And then we can see what is missing. So we look basically for absorption measurement. And such a spectrum is shown here. They are called the Fraunhofer lines. One has, of course, also been careful with this type of spectra. If you have white light incident on a glass, you have, for example, a glass that is yellowish, means there is a lot of sodium in. And on the other side of the prism, you don't see sodium. It might be also this absorption happened in the glass. So you need to use different glasses. And well, this stuff is now named after Joseph Fraunhofer. Oh, that sounds to be very Bavarian, so rather Sepp Fraunhofer. He was the first to realize about these lines. Why? He was an instrument maker. So, very versatile person. And obviously he was the first to try it. And then he has seen, oops, there's something missing. And then obviously bypassed the scientists or what wants to be scientists that publish this. So, of course, what I would tell you, if you look at sunlight with whatever instrument ever, even the bare eye, don't do it. Don't look with the bare eye into the sun. Don't look with a magnifying glass. Don't look with a binocular. Don't look with anything directly, because your retina is not going to like this. We all know this when one looks directly in the sun. We all did. But then you look away, you have this flickering. So try to avoid this. What can you do is, of course, instead of your eye, you take a sheet of paper and put it in the focal plane. So you can go forward, backward to see that you will get a focusing event and then you can see it. So next time there's a sun darkness, especially there, you should do it. Directly look in. So there, use whatever, use a binocular that you nicely adjust on the sheet of paper and you will see it. And without any danger. So, of course, this was here around 1850, 1880. Nowadays, one has a different observatory like this National Solar Observatory of the Yanks in New Mexico and Arizona, so two of them. Then you get a bit of this 2- or 3-dimensional effect that we have when we use both of our eyes. Well, it looks obviously a bit like almost like a weapon, I would say, but it's an observatory. Why New Mexico and Arizona? Obviously, these are southwestern states in the US where there is loads of sun and not too many clouds. Of course, nowadays we have also a lot of probes. One of them is very heat resistant and is now investigating the sun from very close. So the structure itself from all the observations, we would say it has a corona, what means some kind of gas seems to be irradiated constantly. It has the chromosphere on the outside, what we see. So it's a direct surface. Occasionally, it shows, we see it down to the photosphere, not completely, but to a certain degree. We see then occasionally sunspots, or dark spots, not really dark, it's just not as bright as the others. Then deeper we have basically, or occasionally we get this prominence, which is some kind of arc of this hot plasma that comes out and vanishes. If this happens, there's also a lot of gas emitted into the solar system medium. So loads of protons coming out. Well, then we get a convective zone where we basically heat up the material below. And then the hot material goes up and cooler material from the surface. How does it get cooler? Well, up here, the radiation process is much better. So it gets cooler and sinks down again. The heating itself, well, comes from the core. This is what we have established, nuclear reactions. So now if you take a more detailed look at the sun from space, like with the ESA solar orbiter. So this picture is then from the ESA. The sun itself, and then you see here this arc. If we make here a zoom in, you see this picture with this arc. But then next to the arc, we see two darker spots, which is then shown here. If we zoom in, the arc itself is here more emphasized. So we see that the surface is not totally homogeneous. There seems to be, it's not one temperature nicely distributed. There are also spots that are brighter and warmer, and spots that are a bit cooler. and slightly less bright. So cooler. Now, if we take a detailed look into this on this chromosphere, or already into the photosphere, what do we see? This bit of a structure with this very bright or brighter stuff, and then cooler. But bright means here 5,700 Kelvin, and dark means 4,700 Kelvin. So still 4,500 Kelvin. Well above most melting points of materials that we have, even aluminum, thank God. And how can we explain this? This is now together with this convection. So if we have it bright, this is basically where the hot gas comes up and the cool gas is now going down, and this here is some kind of border region between this kind of stuff. So on the inside, the hot material comes up, and on the outside, the cooler material goes down. Oh, this is, by the way, we can make it very nicely homogeneous heating up a cooking pot. And it's a relatively viscose liquid in the pot, what builds a similar structure up. So one gets basically zones where the system reorganizes itself, and we get these zones. And the hot material comes up, and then between the hot zones, there is then these other zones where the cold material is sinking down. Okay, so we basically get now, and that is quite interesting. We have this plasma. So a gas of charged particles, mostly protons, electrons, of course, if they are detached from the hydrogen, occasionally these alpha particles or helium ions. And we have no circular currents of charged particles. This immediately gives rise to magnetic fields. The scientific field that deals with this is called magnetohydrodynamics, so magnetic water dynamics, so liquid dynamics. Of course, this is a dynamical system, and from this point of view, very hard to calculate and chaotic. So small changes to completely change the long-term development of the system itself. Okay. And occasionally what happens is there are these darker spots, which we call sunspots. Well, we all know how spots can be. We were in the puberty, and one spot could spoil the entire weekend. Now we have small viruses that spoil entire years. But once they are gone, there is another dictator that our sun that spoils another year. And, oh. Okay, so these are then a bit cooler. Again, you remember these darker zones were 4,700 Kelvin. This would be also roughly 3,800 Kelvin. These sunspots that occasionally occur. Well, this is now North Pole, South Pole of the sun. So North Pole down here up is the South Pole. But then interestingly, they seem to occur always as pairs. 1 second, 1 second, one, and the other. Pairs, this is almost something you have a North and South Pole, or something that is connected. Then we see there seem to be rather nearby the equator, not so much at the poles. And people were now observing them for a long, long time. So we have the data going back to 1875. Even well beyond. And what do we see? This here is now the north, 90-degree north pole, south pole, 30-degree north and 30-degree south. This is basically where they appeared and when. Then we see there seems to be some kind of cycle. First, they appear here more, a bit more at 30 degrees, and this seems to shift then towards the equator of the sun. Down here, we see basically the numbers in a given cycle, and we see, oops, they come and they go, they come, they go. And the sun has an 11-year cycle, where this seems to happen, at least the last 150 years. But then we also see there seems to be, this year seems to be relatively regular. Then an increase, a decrease, increase, decrease. What is going on here? So if we plot this, one sees there were observations beforehand. So that around 1800, there was a minimum. If we say this is the baseline, here we have the model maximum. We have the Mondor's minimum, or Mondor minimum, around 65. But there might be also observatorial reasons. Back then, can we trust this data so good? Or there's always a question when you get data, how good is it? And it's a matter of honesty for scientists to say these are the weaknesses in the data. At least for me as experimentalist, to be honest with my colleagues from theory. So if we would now assume here, obviously, I would say this is no data that seems to be from the quality the same. Obviously, one benefits also from the technological development. So it might be here that we observe now more of these freckles, more of these sunspots, because our instruments are better. Some that previously might have went undetected are now still there, or are now still observable. So this is another effect. We have to be very careful. Well, there are then now people that, of course, then say, this here is the period where we really realize there's something going on our planet called global warming. But then if one takes this data, or the temperature rise and compares here, there are some people that say there is a correlation. And it's the sun and enhanced sun activity that makes it hotter here. Yet I don't really see there so much of a nice correlation. Here might be one with this bit of bump. So there might be some influence, but there are other things that correlate much better from the curve. And this is, for example, if we look about the carbon dioxide content in the atmosphere due to the burning of coal and nowadays gasoline and even Russian gas, then there is a much better correlation. Yet, of course, there might be also influences. There might be also influences due to volcanic eruption, which always bring a lot of carbon dioxide out. But I think the major stuff is man-made, and we can see this in the isotropic composition. Usually the carbon that is on the surface of the Earth It's mostly the stable isotope or stable versions, what it's carbon-12, where we have 6 neutrons to the 6 protons. Carbon-13, where we have 7 neutrons to the 6 protons. And there is a small tiny fraction made above the poles, which is carbon-14. Carbon-14 is radioactive, has about 40,000 years, and then half of the stuff is gone. Or is it 8,000 years? Sorry. This forms of an equilibrium with the other isotopes. And every biological body that eats carbon or consumes carbon, plants via the photosynthesis. We then, because we eat plants, or we eat animals that eat plants, has their equilibrium until you die. This ratio is, of course, also oscillating a bit or not super constant. But the last 200, 300 years, it's going so much down, the carbon-14 content, because we release all this other carbon that used to be stored under Earth and therefore away from the carbon-14 influence. So this becomes so much more, and the carbon-14 ratio goes down. But the last 200, 300 years, this carbon-14 method that is used to date artifacts is no longer reliable. So, okay. But now we have seen that there are always these pairs. Can we explain this? Is there a mechanism that would say why it's just in this very specific region, mostly? And why always these pairs? Why? What is going on there? Well, so to come back to our sun also has these magnetic fields. Now, obviously, these convective currents that create magnetic fields. They can be locally, but they can be, if we then add them all up, there will be also one very big one. And now we let the sun rotate and look from the north to the south pole. And then we look at a position that is up here, where the circle is relatively small, compared to the equator, and a point on the surface of the sun at the equator, compared to up here. We know the rotational period is the same, but it takes the same time that the sun rotates once around this north-south axis. So now we remember that the circumference of a circle was 2 pi the radius. So the point up here has obviously much smaller radius and a smaller circumference to go, while the one point at the equator has a much, much longer. Then we have a friction. What can happen is now that these currents in the center go loose. Basically, because of the friction are trailing behind, and with them, the part of the magnetic field line that is created is also almost basically trailing behind. But now magnetic field lines don't like to be stretched. They like to go the shortest way. So you should start, if this would be a rubber band, we would basically pulling on the rubber band. And pull and pull and pull, and what happens? Usually at some point the rubber band would snap and break. That cannot happen with a magnetic field line. It always needs to be a circle because there are no magnetic monopoles. So north and south pole are always together. For the elementary magnets, sorry. So the magnetic field lines are always connected, even if we just see them coming out here and entering maybe here. Inside, they are still connected. So, okay. So, but now we twist and twist, and at some point, well, if it cannot break the rubber band, at some point we might not be able to hold it. And then it will snap back to its original position. So we basically twist and twist and twist. At some point, it snaps back. And that might come, it might then come out of the surface of the sun and build there an arch with a field line going out and in. And while it comes out, it also takes a lot of material. You remember, charged particles have the tendency to be trapped by field lines. This is this Lorentz force, which then makes them, forces them to gyrate around the field line. So when it minimizes its length, it stretches back. It might then come out of the surface. And all this material that is gyrating around is coming out with it. So this creates this massive arc. And because the material here is very fast, we have here enormous temperatures. And if this snapping process goes basically too fast, what can happen is that the material, this works a bit like a slingshot or catapult for the material that is trapped here. And this is going to be ejected into space as so-called solar wind. So in order to reorganize itself with the shortest field lines, we might get here this snapping back. And this is, of course, then mostly where it has been most stretched, nearby the equator. This differential rotation leading to the stretching of field lines, this is somehow the best explanation. Well, and then we get these sunspots where the field lines basically come through the surface. Here it's now set 4,500 Kelvin. Before I had 3,800 Kelvin, but this just tells you again the uncertainty in these measurement processes. So this here has, of course, this gas trapped around, which is one part of the solar wind. Interestingly, this seems to be relatively isotropic, what means the same in every angle. Iso, the same. Tropic, this means is related towards the angles. So, but then here we get some kind of minimum where not so much material is coming out near the equator directly. Okay. Well, this is here now the minimum, but obviously if there's a maximum, there might be then rather the stuff come out here. The sun itself is like that. Obviously, south and north pole, magnetic wise, might be twisted around. So we often have, because in the Earth, north is our magnetic north pole almost coincides with the geographic ones. Geographic is basically defined by the rotation. Because this almost coincides, we would now associate North Pole as we have basically called the magnetic North Pole, and the other one South Pole, where the field lines emerge and where the field lines again go into the magnet. By the way, interestingly, if we split the magnet in part, we get a north and south pole, and we get a north and south pole. So we will always have these two poles. If you find a magnetic monopole, just a magnetic south pole, or just a magnetic north pole, you get the Nobel Prize. So the sun constantly evaporates, mostly along, of course, these field lines, where again we get it accelerated. Charged particles want to be always in the region with lowest field line density, so away from the surface of the sun. Along, and they are trapped in this field line, so mostly along the field line. And sometimes they might then start or be able to escape. And this forms the so-called solar wind. So constantly charged particles, protons mostly, evaporated from the surface of the sun. We have evidence for this type of behavior? Of course. One of them is the so-called, or are the tails of comets. Comets are basically dirty snowballs that originate either from Kuiper belt or Oort's cloud. There might be a collision of two bodies, and the one is deflected to a trajectory that goes towards the inner parts of the solar system. Then this dirty snowball, which we know, for example, from the Cassini mission that landed on one and investigated what does the stuff is built of. Then there was another mission. They shot a big block of metal into one of them and then analyzed the debris that was coming out. So we know these are basically water, snow, or ice with loads of dust in it, other dirt. Well, that played a massive role for the young Earth because the young Earth didn't have water. The water that we have on the surface of our Earth is coming in the period of early bombardment when the solar system was created. There were a lot of these dirty snowballs, and they basically bombarded the Earth and brought us our water. Not too bad, thank you. And just the right amount so that we have basically oceans, which we need for life to develop, and that we have still land, continents or islands. At latest, when we look for technological civilization, this is usually only happening on land. Why can I be so sure? In the moment, if you're a sea-based life form, then you discover electricity. We have already one problem underwater. And then you might perform a high-power electrical experiment. Underwater, you do this usually once. You won't do it a second time. So simple is it. So small, you look at the boundary conditions set by physics or basic experiences, and then you know, okay, this is not possible. So in order to create life, usually we need oceans, and then the life needs somehow to come to the land in order to go further with technology. Okay, and these dirty snowballs, when they come to the sun, of course, the sun shines on them, and since if they don't rotate, even if they rotate, they get hot. And then, of course, if you have water to make it hot, or ice, you make it hot, there will be always some small fraction, even if it's just a small fraction, something will evaporate. Oh, and then, of course, when you move, you the stuff is still the same momentum mostly, so it will come mostly move along with the ball, but build some kind of coma. So some kind of slight small atmosphere, but it has to be very careful because the gravity of the object itself, because they are so small, if they're a couple of kilometers wide, if at all, how big is there the gravity? This is a massive problem when you want to land something on them, because you come down with a certain velocity, and then you basically bounce off. That's it. Your probe is back into space. If you really want to land, that's a very tricky process. And the graphist is usually so far away, you cannot just sit here on Earth with the joystick and steer the stuff, because there is now again a delay of a couple of minutes between communication with the probe and the response signal of the probe. Oh. So this needs to go automatically. Okay, now we have this coma, and there comes now two types of radiation from the sun. So it comes close, we get the coma, and there usually we observe two tails. So here's a nice picture. I don't remember which comet this was, but the sun is irradiating from down here. It's moving towards the left. So you might get here a bit of a dust tail, but what one usually gets is directly away from the southern tail, and one that is a bit bent. The one that is bent is usually brighter. This here is the photons, the light particles that come along. You remember light particles make a push, and if you have gas, atomic, smaller particles, then this might be sufficient to push them away. But this also is coming from the sun, this solar wind, so this hydrogen, usually nuclei, so protons mostly. If they hit now on these particles, mostly then also the molecules, of course, they hit, give them momentum, but they are usually bent in the magnetic field and come from a different direction than the light particles. So they come not directly from the surface everywhere, they come often a bit above the surface, they start to get bent, and therefore they come with a different direction. And therefore push the gas and also dust particle. They have now these are bigger objects compared to a photon, which is massless. And pushes basically this dust away in a different direction. And we always will see they point away from the sun. So on the trajectory, it's always pointing away from the sun and not along the orbit of the comet. Comets are quite frequently. As I said, back in the past, they were quite okay. Nowadays, we would like to have a super big one of them impacting on Earth. Okay, another evidence is quite beautiful to look at. For the solar wind, it's quite beautiful to look at. It's the aurora borealis. Here, the northern lights, at the South Pole, the southern lights. What do we have there? Well, these nice shine or lights in the upper layers of the atmosphere, usually seen at night. But this was here obviously a summer night, and I think that must be the ring of Brodgar. So I think it's on Orkney. Oh, so that's a nice picture that fits here nicely. Up. And what is the explanation for this? Well, we get now all these protons traveling towards Earth. There would now a certain amount of them would hit Earth, but Earth is lucky because Earth has a magnetic field. Why? We have a hot core. We have iron that goes up in convective currents. We have a hot solid core, and above is a molten core. In this molten core, there is loads of iron. Iron is a very good magnet. And this is now heated and goes up and comes down in convective current. But this creates our magnetic field. Lucky us. Why? You're going to learn next week. So now the protons are basically getting to be trapped in these field lines and then start directed around, and some of them, they start gyrating around and come then hit the atmosphere at the poles where the field lines goes into the atmosphere. Usually they are well above the atmosphere. This magnetic shield is called basically the Van Allen belt. Okay, so basically they hit here now these charged particles, often even relatively fast. So for me as nuclear physicist, I would dream about occasionally these energies. There they hit now the molecules of the upper layers of the atmosphere. Some nuclear reactions, but what mainly happens is that they either ionize some of these molecules or just excite an electron to an upper level, and then it jumps back. And what we often see is that this greenish light that we associate with nitrogen molecules. So this is basically the process. We have these electrons, ions that now hit the upper layer of the atmosphere, excite there basically the atoms or molecules mostly. And when they de-excite to the most stable, they emit this light, the northern light. Well, consequence of this is an enhanced environmental radioactivity near the poles, enhanced mutation rate. Mutation sounds always bad, but mutation is also a driver of the evolution. And what happened occasionally, the North Pole or the magnetic North Pole was not always at the North Pole. In fact, our magnetic poles occasionally twist around. So, and what you get then is, of course, this region where more radiation is somewhere else. And our magnetic field is not so super homogeneous. In fact, just on the Atlantic Ocean in front of the coastline of Brussels, there is a relatively weak spot that's called the Southern Atlantic Anomaly. When well, who is less protected from this radioactivity are the astronauts, for example, on the International Space Station. I wonder now what will happen to the ISS. So they get more bombardment. What they occasionally see is when they sleep or have their eyes closed, that the water in the eye is so-called scintillation material. So this charged particle interact with this water and make their light flashes. What one gets to this usually a higher rate of mutations, what means mostly cancer, but occasionally also driver for evolution. Well, in terms of technology, too much solar wind can damage or even wreck the electronics. of satellites. So occasionally there's then this switching, the sun is too active, and what are we doing with the satellites? And they need to be shut down for a while. And oh. Okay, we have seen basically, thanks to seismic waves, earthquakes, or an evil dictator in North Korea explodes, makes a nuke test, and we get also seismic waves. From them, we know relatively well about the interior of our sun, of our planet, the Earth. So the North Pole, geographic, and the magnetic are a bit different. At the moment, it's randomly the last couple of 100 or 1,000 years that they almost coincide, but this is not necessarily given. So even if they don't twist, what will happen is that the aurora borealis is no longer observed in the north, so it might be in the Atlantic Ocean somewhere, or somewhere around the equator. So, but otherwise, I would see this as a super dangerous stuff. It would be crap if we wouldn't have a magnetic field. Still, the atmosphere would protect us from all this solar wind. But there are other processes that we talk next week, because it's basically a super recycler. So about the internal structure, we know we have the solid inner core, mostly iron nickel, and then we have this molten iron nickel core, where we have basically again this convective currents, which creates then the magnetic field. So a natural protective shield. So if we don't have this shield of atmosphere and magnetic field, like for example, these guys here, Apollo 11, they went out to moon and back, what takes about 3-4 days, a week. And for them, they have left the Van Allen belt. They have left basically, of course, also the atmosphere. They got a higher radiation dose. In fact, they got a radiation dose that is comparable if a worker in a radiation exposed job like a nuclear power plant gets this. This corresponds to the annual allowed dose. The rest of the year, the worker would not be allowed to go into any radio protected areas anymore. If you fly to Mars and you do so for a year or two, and you're exposed to this stuff, there's a solar eruption. You go a very high risk to be exposed to very high radiation, especially this high energy particle radiation is a dangerous one. All neutrons are also, but they are less prevalent. So this high energy particle radiation. Oh. Seemingly there was an experiment with rats. Rats are smart animals, cage, you show them where they can get their food and then it's fine. They usually easily find it. But now the rats got irradiated with heavy ions bombardment. So this time they started to have problems with their orientation. Turned out these rats got demand. So if you fly to Mars and back and come here, you're probably completely demand. Or if some extraterrestrial come to us, they are probably leaving a steel container called spaceship. They're probably very smelly because if you have a lot of beings, biological beings in a confined space, it usually starts to smell. And then very likely they are demand. Even if you have only fly through intergalactic, so between the galaxies, you have only one atom per cubic meter. You fly through so many cubic meters that, and if you do it fast, what means in your rest frame, the particle is coming very fast. Oh. So RP issues, radio protection issues, if you want to go fly through space. But with this, I would say no. Stop this video, and then we have a bit the working of our sun. So we go now, where do we know how old is our sun? How old is our solar system, roughly? Okay, this will be the next questions in the next video. See you then. Bye.